Hi folks, this is Dr. Rutner, and this is going to be the video walkthrough for the two-sample independent samples t-test with unequal variances. We're going to take a look at the assumptions for the test, how we formulate the hypotheses, state rejection rules, and then we're going to walk through all the computations start to finish. So this is the situation we're looking at. We are doing a hypothesis test for the means of a numeric variable, two populations. We're comparing the mean of one population to another by looking at some sample data. We have to make the assumption that the samples are independent of one another. We have no way to match up items in one sample with items in another sample. We need to make sure that we can assume those samples were randomly drawn from their respective populations. We need to be able to assume that the populations are normally distributed, or that we have large enough sample sizes, at least 30, so that we can rely on the central limit theorem to tell us that we have a normally distributed sampling distribution that we're pulling from. So those are kind of the base assumptions, and these are the same base assumptions that we had with our pooled variance t-test. The place where we are different here is that we can no longer make the assumption that the variances of the two populations are equal to one another. And so what you'll see is that changes two things primarily. It changes the way we compute degrees of freedom for the test, and it changes the way we compute the standard error that goes into our test statistic. So let's take a look first of all at some basic hypotheses, and you'll see these are actually the same as we were looking at for our pooled variance t-test. We're still hypothesizing about the difference between population means. We can do an upper-tailed or lower-tailed one-tailed test, and so you'll see if we are formulating our alternative hypotheses as a less than hypothesis, then we put our region of rejection in the lower tail of the distribution, and we state our rejection rule that we're going to reject the null hypothesis if our test statistic, our sample value, is less than that negative value of t. And then for the upper tail test, we just flip it around. We're hypothesizing about the difference between two population means being greater than some constant value, which is usually 0. And in this situation, we put the rejection region, the whole alpha value, in the upper tail of the distribution, and again, formulate our rejection rule correspondingly. We can also do a two-tailed test where we're hypothesizing for the null that there is no difference between population means, for the alternative that there is some difference. And that would cause us, formulating a hypothesis like that would cause us to split our alpha value between the two tails of our distribution and state our rejection rule in such a way so we're going to reject the null hypothesis with either extremely low values or extremely high values that fall under one of those two tails. So I think fairly straightforward way of setting up our hypotheses here. Let's take a look then at some of the computations that we'll be doing. Now here's where things do get a little bit hairier. Let's focus on the first of these formulas to start with, and what I think you'll see here is that this should follow basically the same pattern that we've seen before. We're computing our test statistic by taking the difference between sample means, subtracting the hypothesized difference between population means, and then dividing by a standard error term. Now in this case, our standard error is computed by taking the variance of the first sample divided by its size, variance of the second sample divided by its size, adding those two together and taking the square root. So those computations, not bad at all. In fact, maybe even a little simpler than our pooled variance computations. Where things get a little bit trickier, a little bit more complex with our independent or unequal variances t-test is the way we compute degrees of freedom for the distribution that we're working with. And so you can see this is actually a little bit trickier. In the pooled variance t-test, we could compute degrees of freedom just by summing the two sample sizes and subtracting 2 from it. Here we have a few more computations to go through. And so you can see what we're doing again is we're taking variance over sample size for each of the two samples, adding those two values together and squaring it in the numerator. Variance over sample size squared divided by n1 minus 1, sample size minus 1 in the denominator. Add that to the same computation for the second sample, sum those up, and that forms the denominator of the degrees of freedom calculation. Now, without even looking at any numbers, you could probably tell that we are not likely to get a whole number result from this computation. Very likely we're going to get some decimal values. And so one thing to be aware of is we're going to follow the normal convention that when we get that decimal result, we want to round to a whole number for degrees of freedom, and we will round that down, regardless of how close it is to the next highest integer value or whole number value. We're going to round down. The reason for that is it makes the degrees of freedom a little bit more conservative that we're using in our hypothesis test. Remember, as degrees of freedom goes down, the area that's in the tail of the t-distribution becomes greater. And so as those degrees of freedom go down, the t-values, the critical values of t that we're looking at, are going to move out a little bit. So it becomes a little bit harder to reject the null hypothesis. So that makes our result a little bit more conservative. All right, so those are the formulas we're working with here. We've also got a formula for our confidence interval, and again, follows the same pattern. Hopefully by now that pattern is starting to show itself or become apparent to you. We are taking a point estimate for the difference between population means. The point estimate is going to be the difference between our sample means. And then we are adding and subtracting a margin of error that's determined by taking a critical value of t, where that is based on 1/2 of our alpha value, and degrees of freedom as we just looked at the computation, and then multiplying by a standard error. So t times standard error gives us the margin of error. We add and subtract the margin of error to the point estimate to form the limits of our confidence interval. And so we'll work those computations in our problem as well. All right, let's take a look at the problem statement here and kind of pick it apart a piece at a time. So we are interested in training, corporate training. This is something that corporations do all the time for employees, as they have training events that they have to go through. And of course, we would like to be able to get the outcomes we want from the training events at a reasonable price or at the best possible price. So we are comparing results that we're going to get from a traditional 3-day training period to a new revised 2-day training period. And we want to look at exit test scores and see whether there's a difference between the two. So we've got 15 people who are participating in the 3-day training, 12 people who are participating in the 2-day training. We're going to compare the exit test scores, and I'm just kind of coming down here to the question. The question that we're going to be addressing is whether there is evidence that the two methods achieve different results. So that's really what we're trying to figure out. Is there a difference between the two? We're going to test this at alpha of 0.05, and we're told that we can assume that population variances are unequal. So we know we have that assumption in place. So let's just kind of walk through this a piece at a time. First of all, our variable that we're looking at are exit test scores. So we haven't seen the data yet, but presumably that's going to be a numerical variable. So we're comparing means of a numerical variable. We have got 15 employees in one sample, 12 employees in another, and we're not provided with any logical way to match those employees up. So we can't do a paired t-test. We have to assume that those employees were randomly selected to participate either in the 2 or the 3-day training. So that gives us independent samples. With 15 and 12 in our 2 sample sizes, we do have to make the assumption that they were drawn from normally distributed populations. We're not given any information about that one way or the other, but just recognizing we do need to be able to make that assumption. And of course, I highlighted down here below, we are also assuming that the population variances are unequal. So just going through those steps, what kind of a variable are we looking at? What assumptions can we make? That should get us into the two-mean comparison with independent samples and unequal variances. All right. Now, the data for this problem I have stored in an Excel spreadsheet, and of course this will be posted out to Blackboard so you can take a look at it and play around with it a little bit. Here are the data points, and again, I've given you raw data in this case, so we've actually got training scores for the 15 people who did the traditional training, as well as the 12 people who did the revised training. And so first thing I probably want to do here is just some basic kind of computations about my sample data. So let me go ahead first of all and pull that together. So I'm going to compute sample size using my count function. All right, we're already told the sample size for the first one is 15, so we're just confirming that and getting it in our spreadsheet. I'll compute the sample mean for those 15 people's training scores. They had a mean of 49.8. Looking at the numbers, gosh, I sure hope that's not a percentage out of 100. So maybe that's maybe scores out of 60 or something. I don't know exactly how the scores are computed, but that's the raw data we have to work with. And then for my sample variance, I'm going to use my var.s function to compute the variance of a sample. And so I get 19.1714. We'll make the same computations for the revised training group. We have 12 of those people. Their mean score is a mean of 52.1667, and the variance of that group, their scores, they have a variance of 25.6061. So a little bit more variability among the scores in the revised group than we saw in the traditional group. All right, so that's just pulling the numbers together. Now, let's go ahead. We also need to state hypotheses and rejection rule and that kind of stuff. So I have that on a little document here. Starting out at the top here, what I've got is just a restatement of the problem, and I think this matches what was in the slide that we just looked at. Then a note here that in the write-up that I've provided for you here, I'm going to be using the subscripts T to refer to the traditional training method, R to refer to the revised training method. I find that using kind of meaningful subscripts like that definitely helps me to keep things straight and avoid mixing up which population and which sample are which. So we are given in the problem statement that the question that we're asking is whether there is evidence that the two methods achieve different results. Not that one achieves better results than the other, but whether they are different. And so with that kind of language, I am looking at a two-tailed hypothesis. So I'm going to hypothesize that the means of the two populations of people who take the two different trainings, that the difference between those means is equal to 0, which means my alternative hypothesis is that that difference is not equal to 0. We are given, of course, sample sizes and a level of significance in the problem statement. And then in my next step here, this is just a restatement of the logic that we had talked through and the assumptions that we had talked through to get us to a t-test for independent samples with unequal variances. So just repeating that. All right, coming down here, the next thing I have is my decision rule. And so my decision rule is stated as we normally state it for a two-tailed hypothesis. I reject the null hypothesis if my test statistic, t-stat, for my sample data is less than some negative critical value or greater than some positive critical value. Of course, I can also state my rejection rule in terms of the p-value and the alpha value. But I wanted to go ahead and take a closer look at this because you'll notice I've got critical values of t here. And this is where we have to start making some computations to determine where those critical values of t come from. So I've actually got those computations down here in order to determine the critical value of t for our rejection rule, as well as for some other computations, we need to know how many degrees of freedom we're working with. And so that gets us into this big hairy formula that we looked at on the slide. And what I like to do when I'm doing these computations in Excel is break it down into smaller chunks. So take a look at this formula and you'll notice a couple of things, I hope. First of all, we've got values that repeat. So variance divided by sample size for each of the two samples appears in both the numerator and the denominator. So that's definitely something I can compute, and I can simplify things a little bit. And then I've also got sample size minus 1 that shows up in the denominator. So what I'm going to do is I'm going to break this down into chunks, and I'll compute variance over sample size for both the traditional and revised trainings. Then I'll do a separate formula to do the numerator of this fraction, and then another one that'll do the denominator of this fraction. Once I've got those computed, I'll do the division, and we'll see if it comes out to be the same number that we're showing here on our write-up. All right, I'm actually going to push that over to one side so that we can see the formula while we're working here. And let's come down in the spreadsheet and start making those computations. So first thing I want to do is compute variance divided by sample size for population 1, or sample 1. And then the same thing for sample 2, variance divided by sample size. So that's easy enough. Numerator of degrees of freedom, that's referring to the numerator of this equation that you see over here. So what I'm going to do is take those two values that I just computed, add them together, and then square the sum. So that will be the sum of the 1.2781 and the 2.1338. Add those together inside a set of parentheses and then square the total. So that gives me the numerator value, the value that plugs in the numerator of this fraction of 11.64 and change. Then for the value in the denominator, again, remember I've already computed variance over sample size. So what I need to do in the denominator computation is take that computed value, square it, divide by n minus 1, and then add that to the same computation for the second sample. So again, not too bad. So I'm going to take my variance over sample size squared, divide by size of sample 1 minus 1, and then add that to the same computation, variance over sample size squared, divided by the size of sample 2 minus 1. So got my denominator value. Now, to get total degrees of freedom, I'm just going to divide the numerator by the denominator. And I believe 21.9393, I do believe that was the same number we had showing on the slide over here, or showing on the write-up over here. All right, now there's a couple ways I could round this down. There's an int function I think we've looked at. The one I'm using in this example is the round down function. You know, of course, one of the nice things about Excel is that it gives us multiple ways to accomplish whatever we want to accomplish. So here we're going to use round down. The arguments I need to give to this function are the number that I want to round. That's that 21.9393. And then the number of decimal places I want to round to. I want to round to the nearest integer. And so I am going to round to 0 decimal places. And so that gives me 21 degrees of freedom that we'll be using for our computations. All right, so with 21 degrees of freedom, and remember we started this process because we wanted to know where these two critical values came from. With 21 degrees of freedom, I'm going to come down in my spreadsheet. I now know enough to determine the critical values that we're going to compare our test statistic against. And so I will use my t-inverse two-tailed function for that. I'll do the upper critical value first. For this function, remember that the two-tailed function when I give it a probability, what I'm going to give it is my whole alpha value, and so that's the 0.05 level of significance. And then I also need to tell it degrees of freedom, and what I will put in here is that rounded degrees of freedom we just computed. And so that confirms the number, the 2.0796 that we have stated here. And of course, I can just take the negative of that value if I want to, or I could recreate the formula as I have it shown here to get the negative of that value for the lower critical value. Either way is going to work just fine. All right, so those are my critical values that I need for the rejection rule. Those are also the critical values, or at least the critical value that I'll use when I compute the margin of error for the confidence interval that we're going to do as well. All right, so that's those numbers. Let's come back and let's see what else we have to compute. I think the next thing that we probably want to do is information that we need for our t-statistic, our test statistic. And so again, let's take a quick look at this formula. In the numerator, I've got the difference between sample means. That's easy enough. I've got the difference between population means, and I just entered that as a value up here in my spreadsheet. In this case, we're hypothesizing that that difference is 0. And so it looks like the only thing really left for me to compute is this standard error. And so I've got a place where we can do that. Now, notice that the standard error computation takes advantage of some things that we've already computed, namely that we've got the variance over the sample size for both the training group and the traditional training group and the revised training group. So that actually simplifies our standard error computation, because what I'm going to do is just take the square root of variance over sample size for the traditional group plus variance over sample size for the revised group. And so that gives me a standard error of 1.8471. And then finally, I'm going to go ahead and just compute the difference between my sample means. I've got the traditional group first, and then subtract the mean for the revised group. And so that gives me a difference of minus 2.3667. All right. So that's all the terms that I need for my test statistic. So now I'll do that test statistic, compute it, by taking the difference between sample means, subtracting the hypothesized difference between population means, and then I will divide by the standard error. And that gives me a test statistic of 1.2813. And I do believe, let me shrink this down a little bit. Yep, that matches what I have on the right up here as well. So that is the test statistic that we have based on our sample data. At this point, I have enough information to make a decision. Recall that our rejection rule said that we were going to reject the null hypothesis either if we get a test statistic less than minus 2.0796 or greater than positive 2.0796. Minus 1.283 actually falls in between those numbers, not greater than or less than, and so we are going to fail to reject the null hypothesis. We will not reject the null in this case. So we will conclude that we don't have evidence to say that there is a difference in the outcomes between the two different training methods. Now, I do want to do a few more computations to support that. I'd like to compute a p-value and a confidence interval. So I'm going to go ahead and continue making computations before I state that decision. All right. So coming back down to my computations, recall that a p-value is the probability of getting a test statistic based on sample data at least as extreme as what we got if the null hypothesis is true. And so because we're doing a two-tailed test here, we need to consider that our test results could be more extreme in either the positive or the negative direction. And so the formula, the function that I'm going to use to compute my p-value is going to be the t-dist two-tailed function. And so let's take a look at that function. And so what I need to do is I need to give it my test statistic. Now, this two-tailed function is a little bit particular. It doesn't like to get negative numbers in this first argument, this x argument. And so in this case, I know I've got a negative number, but I can take care of that just by using my absolute value function. So I'm just going to put that cell reference for the argument into an absolute value function. And so that way I've got a positive value that is going to be used as the argument for t-dis two-tailed, and then degrees of freedom is the same degrees of freedom that we had calculated a few minutes ago. What this function will return to me is the probability of having a test statistic or a value that is either greater than 1.2813 or less than minus 1.2813. So more extreme than my test statistic in both the positive and negative directions. All right. The p-value we get is 0.2141. And if you recall how we stated our rejection rule in terms of p-value, we'd reject the null hypothesis if we get a p-value that's less than alpha. 0.2141 is not less than alpha, and so that confirms our decision that we're not going to reject the null. Now, I like to actually write an if function in my spreadsheet here, and I find the easiest way to do that is to base it on the p-value once I know how to compute that. So that's what I will do here. And so my logical test is going to be that I'm going to take that p-value, compare it to my specified level of alpha, and then if that comparison comes out to be true, we will reject the null hypothesis, otherwise we fail to reject the null hypothesis. And so I can verify my results there and see that sure enough, we're getting fail to reject coming up. All right, last thing we're going to do, and last thing that I have shown on my little write-up here, is we're going to go ahead and compute the confidence interval. And remember, for the confidence interval, we take our point estimate for the difference between sample means, add and subtract margin of error. That is based on the t value, the critical value of t for alpha and or 1/2 of alpha, and then in this case 21 degrees of freedom that we computed previously, and then multiply that t value times the standard error of the distribution. Good news is all the pieces again are already computed for us, so it's just a matter of putting them together. So for my margin of error, I can compute that by taking my critical value of 2.0796, multiplying by my standard error, and that gives me a margin of error of 3.8413. And then my lower confidence limit is going to be the difference between sample means minus margin of error. My upper confidence limit is going to be the difference in sample means plus margin of error. So what this tells me is that with 95% confidence, because we had an alpha level of 0.05, remember, with 95% confidence, the true population difference between, or the true difference between the population means, it's probably a better way to say it, the true difference between the population means is somewhere between minus 6.208 and positive 1.4747. The hypothesized difference of 0 falls within that confidence interval, and so that confirms our decision that we do not reject or we fail to reject the null hypothesis. So we worked through this problem, we've done all the computations, we have compared our test statistic to critical values, we've computed a p-value and compared it to alpha, we've computed confidence intervals and compared it to the hypothesized population mean, and we're getting the same results from each of those approaches. Each of those approaches is telling us that we will not reject the null hypothesis for this problem. So I think I'm feeling pretty confident in our results. Just writing out that decision and that conclusion here, we fail to reject or do not reject the null hypothesis. with 95% confidence. Another way I could say that is at the 0.05 level of significance. There is not sufficient evidence to conclude that there is a difference between exit exam scores under the two training methods. All right, so that wraps up independent samples with unequal variances. I'm going to go ahead and stop this recording here, and we will have separate recordings for some of the other methods.